Okay, so this is the last video, video number 3 on thermodynamics and equilibrium. And so basically we're going to continue our thought on how to calculate delta G. But before we do that, we're going to take a short break and talk about how we or why we even care about delta G values. So a lot of times we have a reaction that we're interested in doing or interested in performing. But a lot of times this particular reaction might be non-spontaneous, okay? And in that case, you're trying to do a non-spontaneous reaction and can't get it done because it's not spontaneous. So what would you do, or what could you do to make it spontaneous? So the idea is you can couple or do two elementary reactions at the same time, and the second elementary reaction that you're going to couple is going to be highly spontaneous. So this is an example here. You've got the reaction of iron 3 oxide. And basically what you want to do is you would like to take the iron 3 oxide that you dig out of the earth. And when you dig the iron out of the earth, it's never pure iron. It's always iron oxide, so iron bound to molecules of oxygen. And you would like to separate the iron atoms and the oxygen, so separating it. So you get pure iron, which you can then use to make buildings and other things. Okay, so if you look at this value here is very positive, positive 1,487. So you would say this is a non-spontaneous reaction. Okay, and so if you were to try and do this in a lab, you would have to, basically you can't do it because it's not spontaneous, okay? But what you can do is you can couple it to a carbon monoxide reacting with oxygen reaction to form carbon dioxide. And this reaction, notice, it's negative 1543. So this is what we call a very spontaneous reaction, okay? And so if you couple these two reactions together, if you add your two Gibbs free energy values, you're going to get minus 56, which is still spontaneous. So overall, your reaction is going to be spontaneous. The net result is to reduce the iron 3 oxide to the metal by reacting the oxide with carbon monoxide. So this reaction that occurs in a blast furnace is where we normally do this kind of extraction of pure iron. is commercially is where iron ore is commercially reduced to iron. So let's see how this kind of coupling and setup works. Okay, you have raw materials, iron ore, coke, and limestone, and it's added to the top of the furnace. So this is your iron ore, this brown stuff here. Okay, this is the stuff you dig out of the earth. Okay. And what you're going to do is you're going to have blasts of hot air, and they're blown near the bottom of the furnace. So here you've got blasts of hot air, and they're being blown into the furnace, okay? Oxygen is being fed into the bottom because oxygen is in the air, so it's being fed into the furnace, okay? And it reacts with the carbon to form carbon monoxide, okay? So you've got carbon in there, and so it forms carbon monoxide here, okay? And this reaction is very exothermic. It produces a lot of heat. It's very, very hot. So here you have like 2,000 degrees Celsius, okay? And as the carbon monoxide, so here carbon monoxide is being produced, okay? Because what you have is carbon plus oxygen, so it produces carbon monoxide, okay? It rises up in the furnace and it reacts with the iron ore, okay? So basically this reacts with the iron ore that's falling, this is your iron ore, Fe2O3, and it's reacting and falling in, and so it's reacting together, okay? That's the first reaction there that's not spontaneous, right? You're, okay, that's basically your first reaction there where you have Fe2O3 plus 3CO gives you Fe plus 3CO2. I shouldn't say it's the first reaction, should say it's the overall reaction, okay? Because what happens is, if you look back at your original equation, your 3 O2s do cancel out, your overall reaction is here, okay? So this is where your overall reaction is happening. This is where your Fe2O3 is reacting with your carbon monoxide. And it's producing your pure iron plus your carbon dioxide, okay? So the iron ore that's being produced, that's this guy here. Sorry, the iron or the pure iron that's being produced is molten because it's really, really, really hot. And so it will run down to the bottom of the furnace, and basically it is tapped out from time to time and collected. And then this pure iron is then used to make all kinds of things, steel and other things like steel girding for buildings and things like that. But really, the idea is you're coupling these two reactions to make it very spontaneous. Okay. This happens in our body as well. We do couple elementary reactions. Okay, so in our cells, we often would like to make large macromolecules. So basically, for example, proteins, DNA, RNA, these things are large molecules, and they're basically small subunits linked together. So if you think about proteins, for example, okay, proteins are really amino acids, and we're going to call them AA for amino acids, and they're basically linked together. And we have lots of different amino acids in our body, and they're linked together in a long chain. And when the amino acids are linked into a long chain and they fold upon themselves, they form proteins or enzymes. Okay? DNA is the same way. DNA, if you're thinking about DNA, it is really, right? If you're thinking about a single strand of DNA, what you have is you have a base pair. So you have a base, right? And that is linked to a, let me write it just a little bit bigger so you can see. So the backbone is really ribose. It's the sugar, right? So I'm just going to draw this as like this. This is ribose. This is your sugar. And it's connected to a phosphate. And then another ribose sugar. And then another phosphate. So on and so forth. And connected to each of these ribose is a base pair, right? So you've got your, if you've got DNA, you've got your A connected to your T. This is your base pair. And then you've got another ribose. This is a very, very general sketch. And then phosphate, and then ribose, and so on and so forth. And you have base pairs. Maybe you have a C and a G. So if you've taken biology, this should be review, okay? Just write it clear. And you can always look in your textbook, in your biology book, to kind of see what this looks like, okay? But basically, you have a macromolecule, okay? And you're basically linking small subunits of ribose, phosphate, base pairs, or you're linking together amino acid, amino acid, amino acid. You know, the idea of fats are the same, fatty acids. You just link together a bunch of fatty acids, right, to get fat molecules. So the idea that you're linking these things together, these reactions are not spontaneous, okay? So to get if you're looking at a cell and you're looking at inside your cell, to go from amino acids to the protein, we are linking together lots of amino acids. And it's unfavorable. It's non-spontaneous. Okay? So what they do is they take another reaction called ATP, and adding water becomes ADP and a phosphate ion. And this reaction is minus 31. It is spontaneous. Okay? So basically what we can do is we can take this reaction here, that is non-spontaneous, Okay, and then we're going to couple it to a reaction here that is very spontaneous. And that's how we get things to be built in our body. In our body, things are built from small particles, and each one of these coupling reactions where we're linking together little bits or little, what they call monomers of amino acids, and it forms a polymer called a protein, is only done because we can couple it to the conversion of ATP to ADP, which is a very spontaneous reaction. And just as a quick review of what ATP and ADP is, notice that there are 3 phosphates in ATP. Here's 1 phosphate, 2 phosphates, 3 phosphates. What you're doing is you're making it 2 phosphates, so 1 phosphate, 2 phosphates. And basically you have a phosphate ion that's separated. All right, so this is just a quick review of coupling reactions and something in biology that we learned. All right, last but not least, we're talking about the third way to calculate delta G. So remember, we've learned the 2 other ways. One way is we just say delta G is equal to delta H minus T delta S. Okay. The second way was we said that the delta G is equal to the sum of the products minus the sum of the reactants. Let's just write this to simplify things. Just say G products minus sum of the G of the reactants. Okay. The third way to do this is what we're going to talk about here, where we get delta G is the result of minus RT ln of K. Okay? And calculating it all of these ways will get you the same answer, or should get you the same value. Okay? So what is this kind of way of calculating it this third way? This third way is to keep track of equilibrium, or bring in the idea of equilibrium into the idea of thermodynamics. So remember, K we learned it all the way back in chapter, I believe, 14, where we said for solutions we use Kc, for gases we use Kp. Okay? And so K is really, don't forget Kc, let's just remember, is equal to the concentration of the products and then over the reactants. Okay, that's how we calculated K. So at non-standard conditions, non-equilibrium conditions, we use Q. And at equilibrium, where delta G is 0, QC equals Kc, so we use K. Okay? So let's look at how we would use this equation to calculate delta G. So example 18.8 from your book. What you have is they ask you to find the value of the equilibrium constant they ask you to find the equilibrium constant K for the reaction where you have 2 ammonias and you're reacting it with carbon dioxide to form urea and H2O. So, they tell you that the standard free energy change delta G is equal to 13.6 kilojoules. So let's write down what we know. We know delta G is 13.6 kilojoules. R is the one of the gas constants, 8.31 joules per kmol. Notice it is joules here. Okay. Temperature is 298, and we were looking for K because they would like to know what is the equilibrium constant K. Okay. Because this is in joules and this is in kilojoules, you must convert your 13.6 from kilojoules to joules, okay? Otherwise, your units will not cancel out, okay? So to do that, you're going to go 13.6 kilojoules times 1 kilojoule, because the larger unit is 10 to the third joules. This comes out to 1.36 times 10 to the fourth joules per, just joules. Actually, just write joules per mole. It's fine. All right. So with that in hand, we're going to then calculate K. And if you want, you can rearrange this equation first into K equals. So we're going to divide this side by minus RT. And divide this side by minus RT. Okay. So this cancels out. So we get ln of K is equal to delta G over minus RT. To get rid of the ln, what you need to do is you need to raise it to the e on both sides. So that cancels out your ln. So this gets you e to the delta G over minus RT equals K. Okay? So we're going to write that here. We're going to say K is equal to e to the, and remember we're going to plug it in. Delta G is now this value here. Okay? 1.36 times 10 to the fourth joules per K per mole. Divided by minus 8.31 joules over K mole. Okay, and then times 298. You need to do all of the things in the parentheses first. So K is equal to 5.49. All right. So let's see here. So then we have to do e to the 5.49. Oh, hold on a second. Let me just see here. There is a typo in here. I apologize. In this problem, it is equal to negative 13.6. So this is a negative value. It should be a negative value. Sorry, I made a mistake. This should be negative. All right, so this comes out to positive 5.49. So then e to the 5.49, and you get 2.4 times 10 squared. Okay, remember K has no value. No units. Its value is no units. So therefore, you don't need any units to include any units. All right. So the next problem that we're going to look at, give me 1 second here. I just need to do something real quick here. So they want you to calculate KSP at 25 degrees, and they give you the equation AgCl is in equilibrium with Ag aqueous plus Cl minus. This is your normal solubility equation using standard free energies of formation from table 18.2. So what you're going to do is you need to pull out your table 18.2, which is your delta G table. The delta G table. It's all flipped to our delta G table. And you're going to find the values for silver chloride. So silver chloride Solid is minus 109.8. I'm going to write it underneath here. 109.8. Okay. Your silver plus is going to be, and remember it's aqueous, is 77.12. Okay. And, sorry, I apologize, this is minus 109.8. And your Cl value is going to be equal to chlorine, Cl minus 131.3. Okay. So with these values, you're going to calculate delta G, and it says to use the standard free energies. So we're going to say products minus reactants. These are our products. This is the reactant. Okay. So we say delta G is equal to, let's solve it. We're going to go 77.12 plus a minus 131.3. Then we're going to subtract our reactant, 109.8. Okay? And if we do this math all the way through, let's see here what we get. We get approximately 55.6, okay? And because the table 18.2, so if we're looking at the table, looking carefully, we're going to be in the units of joules per kmol, okay? So now we're going to in joules or kilojoules. Let me just double check real quick. 77.12 minus 131.3 plus 109.8. Yes, we are in joules per kmol. Okay. So then we need to solve for K. And again, K, let's just rearrange it again. So minus RT. So this cancels out. So my ln of K is equal to delta G over minus RT. So let's plug everything in. Ln of K is equal to 55.6 joules over kmol divided by minus 8.31 joules over kmol times the temperature. The temperature is 298. Oops. Temperature is 298 because it is 25 degrees. You know something? I did the thing that I just told you guys not to do. I used S values instead of, I think, G values. Let me just check real quick what I did here. Yes. Wait. Let's see here. Did I use the wrong values? No, I didn't. I'm okay. But I am in the wrong units. I apologize. This should be in kilojoules per mole. Looking at the wrong table. Kilojoules per mole. Okay. Yeah, that makes more sense because I need to first convert this value from kilojoules to joules. So I'm just going to do that real quick here. 55.6 kilojoules per mole times 1 kilojoule, 10 to the third joules. So this comes out to 5.56 times 10 to the fourth joules per mole, which goes here, 5.56 times 10 to the fourth joules per mole. Okay, sorry about that. All right, now that we have the proper delta G with the proper units, what we're going to do is we're going to cancel out our joules, our moles, and our Kelvin. Okay, and so ln of K is equal to minus 22.45. And we're going to raise it to E on both sides so that the ln's cancel out. So K is equal to 1.8 times 10 to the minus 10. All right. And when this is a very, very small number, we know that at equilibrium, this is going to be mostly reactants instead of products. All right, last but not least, we're going to look at when free energy is not at 25 degrees, and they can be calculated according to the equation delta G of T equals delta H minus T delta S. And basically, by assuming that enthalpy and entropy are constant with respect to temperature, this is somewhat true. So let's look at an example, 18.10 from your book. And so basically what it's saying is, what is delta G at 1,000 degrees Celsius for the following reaction? And they say to use the table 18.1 and 6.2 to calculate the enthalpy and entropy. And then they ask, is this reaction spontaneous at 1,000 degrees? And so you're just going to do the same thing. You're going to calculate delta H using your products minus reactants. And you calculate delta S using your products minus reactants. And then you have to calculate this. So basically what you're going to do is you're going to go delta G. So if you had calculated from 18.1 and 16.2, you're going to get delta H is equal to, let me write it here, 178.3 kilojoules. Oops. Okay, and if you calculate the delta S, you're going to get 159.0 joules per K mole. Okay, so again, you're just doing products minus reactants to get those two numbers. Okay, then what you want to do is you want to calculate G at a specific temperature, not at 25 degrees. So let's do that here. You're going to get delta G of T is equal to, where are we here? Delta H. So let's just plug in delta H actually, because we know what delta H is. Delta H is 178.3 kilojoules per mole. Okay, and we're going to subtract, and T is 1,000 degrees plus 273, so 1,000. I was making so many writing errors. 1,273 Kelvin. Okay, and we need to convert our delta S into, I'm going to convert this into kilojoules. So we're going to divide by 1,000, so we're going to get 0.1590 kilojoules per mole. So that we're going to plug it in here, 0.159 kilojoules per mole. okay, per kmol, sorry. And the reason for doing that conversion is so my kelvins cancel out and I can do kilojoules per mole, subtract kilojoules per mole. And so this comes out to minus 24.1 kilojoules per mole. Okay. So, if you raise the temperature a lot, obviously you are making it more, the delta G value more negative. And so basically you can make it spontaneous by raising the temperature to like 1,000 degrees Celsius. Of course, you have to figure out a way to raise your reaction to 1,000 degrees Celsius. All right, part B says, what is the value of Kp at 1,000 degrees? So you need to use your delta G equals RT ln of K. Remember that what you have here is we need to solve for Kp here, right? So basically you're going to say, okay, delta G is now equal to, so delta G at, let me write this down, delta G at 1,000 degrees Celsius is equal to minus 24.1 kilojoules per mole, which is what you solve for, right? Your R is equal to your 8.31 joules per kmol, and your T is equal to 1273 Kelvin. Okay, so really you're solving for Kp, and again you're rearranging this equation. You're going to divide this side by minus RT. You're going to divide this side by minus RT. So you're really solving, this is your no. Okay, to solve, okay, you're going to go ln of Kp is equal to delta G, which is over minus RT, which is equal to, and again you need to convert because this is in joules, this is in kilojoules. You need to convert it to the same units. I would again convert this to to joules. So you're going to divide by 1,000. You're going to get 0.0241 joules per mole. Okay. So then you get minus 0.0241 joules over mole, J, all over 8.31 joules over kmol times 1,022.73 Kelvin. Okay, so if you do this math all the way through, I made a mistake. I need to, this is why you should write conversion fractions down. 1 kilojoule, 1,000 joules. So it's going to be minus 2.41 times 10 to the 4th joules. Yikes, that would have made the math very, very different. Minus 2.41 times 10 to the 4th joules per mole. Okay, so this comes out to let's see here, 2.278. So ln of Kp is equal to 2.278. Okay, you're going to raise both sides to E to get rid of the ln. So Kp is going to equal 9.8. Okay, at 1,000 degrees Celsius. All right, as you can tell, it's really important to keep track of your kilojoules versus your joules, converting it correctly. You can even see that when I was doing it, I went in the wrong direction and then caught myself. It might be always good to write this kind of conversion factor down for make sure your units cancel out so that you don't make a mistake. Here again, you should, again, convert to the same units to be able to plug it in here and here. I think that is the most common mistake that people make. In fact, you've seen me make minor ones here and then catch myself or correct myself. I would say this, when you're doing your homework, it might be good to go through, write down your units, be very faithful about writing down your units, and then, of course, as I always tell you, go back and check your work. Go back and check your math. Go back and check to make sure you didn't drop like a negative sign. You didn't forget to bring down a stoichiometric coefficient when you're calculating delta H and delta S. So really the last slide is saying free energy, okay, at non-spontaneous conditions really does depend on temperature, okay? So if, for example, your delta H is negative, your delta S is positive, then your delta G should be negative and should be spontaneous at all temperatures, okay? This is fairly true, okay, for, fairly regulated temperatures, okay? And if you have something that's positive and positive, delta G is positive or negative. It really depends on whether you have high or low temperatures, okay? So this is really what we're saying here in this table, right? If you have delta G is equal to delta H minus T delta S, okay? If this is negative, this is positive, right? It's going to be spontaneous because you're going to get a negative value here. And when you have negative positive, you're also going to get a negative value here. So a minus value and a minus value, you're going to get a minus value. So it's going to be spontaneous. Okay? That's the first scenario there listed here. That's this number one. Okay. Number two, let's do number three first, because it's let's see here. Spontaneous. Okay, let's do the second example here. The second one says, if this is positive, okay, and you have a subtract a negative, right? Because this is negative. Then this becomes plus and plus, so this becomes plus. So when you have this kind of situation, it is not spontaneous. Okay? We're just looking at signs. We're not looking at values. It's just signs, because if this is positive, if the delta H is positive, the delta S is negative, negative and negative becomes a positive, so it becomes positive. Okay? These are the two unambiguous situations. Okay? The third situation becomes ambiguous, because if you have negative and negative, okay, and this is also negative, right? Because, whoops, not circled. It's just negative, okay, because of this situation here, okay? Then this together becomes positive, right? So depending on whether the temperature is high or low, right? If this temperature is high, then this number is very, very big. And so then you get positive values, right? If it's very, very small, then you get very small numbers and it becomes negative. So that's why it says spontaneous at low temperature, not spontaneous at high temperatures, right? Because if this is if T is very high, then this value is large. Okay, then it's going to be very positive, and then you get non-spontaneous. If it's very small, it's vice versa, then T is very, very low, then you get spontaneous. Okay, the last situation, again, is like that. You have something where it's positive, and then you have minus a positive value. So this can be small or large. Again, if it's low temperatures, you're going to get non-spontaneous. If it's high temperatures, you're going to get spontaneous. Okay? So really this table on the right-hand side here kind of sums up what we talked about here. I found this on the internet. Sums up what we just said. Ultimately, on an exam, you wouldn't be asked to predict it, but you would be asked to calculate delta G. And again, there are 3 different ways to calculate delta G. Where is it? Where did I write it down? Here. There are 3 different ways to calculate delta G, and you will be tested on all 3 ways. All right, that ends this video. Sorry for all the different interruptions that we've had. I did get a couple of phone calls during this time, so I apologize. And I also apologize for using the wrong units in one of these problems and then having to correct myself. But ultimately, hopefully that will allow you to see where some of the common mistakes are. And so really check your units, make sure they cancel out, check your math, and make sure you don't drop any negative signs. And then also when you're calculating like the sum of the products minus reactants, make sure you bring down your stoichiometric coefficients so that the calculation is correct. All right, good luck with your homework. You should finish your homework all the way through for chapter 18. And I will see you in the next video for chapter 19 on electrochemistry. All right.